So I'm going to apply that angle addition formula to this right hand side of this expression. So that's going to, and because this is just a times that mess, I'm just going to treat it like a distributive property. I'm going to say sine of x cosine of theta plus the sine of theta times the cosine of x. And then I can distribute that a through, so a times the sine of x times the cosine of theta plus a times the sine of theta times the cosine of x. So this has to be equal to that right-hand side. And then what I'm noticing, wouldn't it be nice if, you see how there's no cosine in this term that's with the sine x? Wouldn't it be nice if the cosine of theta was equal to 1? The angle, whatever angle that theta is, that we want the cosine of it to be equal to be 1. So that way we just have the sine x left. So that's what I'm going to do, is I'm going to break this part up into these separate pieces, and I'm going to say a sine x times the cosine of theta has to be equal to negative 3 sine x. So now, if I break a little bit of a rule that I like to impose on myself, I'm going to divide by the sine of x, because I've got a sine of x on both sides. And yes, I'm losing a 0 normally, but in this case, that leaves me a times the cosine of theta has to equal negative 3. So then if I divide by a and I divide by a, that tells me the cosine of theta equals negative 3 over a. I could say a sine theta, because here I'd like sine theta to be equal to 1. Cosine x equals 5 cosine x. Well, if I divide both sides by the cosine of x, that leaves me a times the sine of theta equals 5. So the sine of theta equals 5 over a. I've got these two pieces. Now, in order for the cosine to be negative and the sine to be positive, that means it would have to fall in quadrant 2. And since sine is opposite over hypotenuse, the opposite side is 5, the hypotenuse is a, and for the cosine that's negative 3 and the hypotenuse is a, and we can use the Pythagorean theorem to find a. So that's going to be 25 plus 9. So this is equal to a squared, of course, right? So a is equal to the square root of 34. These two relationships going on, and I'm just going to find the arc cosine of negative 3 over 34. And when I did that earlier, did I do it earlier? I guess I'll do it here. So arc cosine of negative 3 divided by the square root of 34, I got 2.111. And that's the cosine of theta. And I could double check here to make sure it's the same. So I'm going to do the arc sine, arc sine of 5 divided by the square root of 30, which should be the same number. So just so you can see what I did, I've got, so here's my arc cosine, that's where I got that answer, and then I just checked my angle to see if it was the same with the arc sine, and that was a mistake. I did the arc sine here, and I came up with that number, and I asked myself, well, those aren't the same number, so what's up? Got to remember that we're in quadrant 2, and arc sine will give me output in quadrants 4 and 3, so this angle is the 1.03, and I know I have to be in quadrant 2, so that'll be the same angle. Remember that those two angles have the same sign, so maybe it would be smarter to go with the cosine if you remember that. But so you got to ask yourself what quadrant the angle falls in, and you see when I took that away from pi, so that's the reference angle. Right, I got to finish my thought here. If I take away the reference angle from pi, then I'm getting the same angle. Okay, so to finish off this problem, so originally we had to write this as a single as a single trig relationship, and that's what we have. And if you go check out, it should be square root of 34, shouldn't it? Sorry. I don't know where I got the 29 from. Square root of 34 times the sine of some angle plus 2.11. Okay, so hope that helps you out. I'm actually will try number. I'll try. What was it? It was 20. It was 37. I'll write out the problem for you. It says we have to rewrite 5 times the sine of 3x plus 2 times the cosine of 3x into a single relationship of a times the sine of bx plus c. If you want to stop this video, try this, and then come back and watch me solve it, you certainly can. So I hope you tried it. What we do know is, if we think back all that other work, is we can expand that out using we can expand out the a times the sine of 3x plus c. I'm sorry, I should have written bx. Well, why don't we leave it there? Because we know we're going to have the 3x. I have to expand that out into what they gave me originally, which is 5 sine 3x plus 2 cosine 3x. And they said bx, so I knew the 3x would be the bx, so that was kind of easy. But we're going to go through that same process of using the angle sum identity. So I'm going to rewrite this left-hand side as a times the sine of 3x times the cosine of c plus a times the sine of c times the cosine of 3x. And I know that has to equal this thing up above. So then, since I can get rid of the 3x, I'm going to say a times the sine of 3x times the cosine of c has to equal 5 times the sine of 3x. So if I divide both sides by sine 3x, that gives me a times the cosine of c has to equal 5. So the cosine of c equals 5 over a. And I know that 2 times the cosine of 3x has to equal a times the sine of c times the cosine of 3x. And again, if I divide both sides by that cosine of 3x, that leaves me 2 equals a times the sine of angle c. So the sine of angle c equals 2 over a. So that gives me these two ratios, and then since both the sine and cosine are positive, that has to happen in quadrant 1. So the cosine is 5 over a, the sine is 2 over a. If we apply the Pythagorean theorem, I get 25 plus 4, and I'm going to take the square root, I get 29. And then I can find the arc cosine of 5 over the square root of 29. And when you do that, you get that the measure of angle C equals 0.381. So that gives me a final answer of the square root of 29 times the sine of 3x plus 0.381. And those check with the back of the book too. So hope this helps you solve this kind of question.